It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Tollen, a nice coffee.
Hi guys, welcome to the third video in the organic chem topic. This one's going to be a reasonably short one. It's section 3.3 on aldehydes and ketones. There's going to be a fair bit of chemistry which we've already looked at and covered in the alcohol section, so hopefully it's just a bit of a recap for you. Now the reason I've got a picture of some perfume on here is that aldehydes and ketones are quite often used within perfumes and as fragrances because they have quite a sweet smell. So aldehydes have the general formula RCHO. Okay, now so obviously it's a different way of writing it than compared to the alcohol, which was OH. So if you see HO, that's the aldehyde shortening. Now it has this carbonyl group in here. This carbonyl group is quite a polar group. You've got a delta negative here on your oxygen and delta positive on your carbon. Okay, so this gives the this group some polarity. Okay, and as a result of that, this functional group can form dipole-dipole bonds with itself. It can't form hydrogen bonds though, because remember the definition for a hydrogen bond is being able to have a oxygen or a nitrogen with a hydrogen attached. So you either need that or you need that. Okay, now this doesn't have that. Alright, it's got a hydrogen or a carbon, so you can't hydrogen bond, but you can dipole-dipole. Now dipole-dipole bonding is weaker than hydrogen bonding, so what that means is that when this aldehyde bonds to another aldehyde molecule, it's going to be held together by weaker secondary bonds than the alcohol. So the boiling points of our aldehydes is lower than the corresponding alcohol. So if we're talking about methanol here, the boiling point of methanol is lower than methanol. The boiling point of ethanol is lower than ethanol. Okay. This also means that their solubility is lower, okay, because they don't have as good hydrogen bonding capability as, say, an alcohol. They're only very partially soluble in water. As soon as you start increasing the carbon chain length, you're increasing the non-polarity of the molecule, and so you're decreasing the solubility in water. What we've got here is the first 5 aldehydes in the series. You can see for aldehydes with all of them that the name ends in AL. Okay, it's a terminal functional group, which means it's always at the end of the chain. Okay, so you can see the carbon chain just increases to the left, but the functional group is always at the end. That means you don't need to bother numbering them when you're actually naming these. All right, so it's just butanal, pentanal. It's not pentan 1L because the aldehyde always has to be at the end. Okay, and like I said, they have a characteristic sweet odor, which is quite often why they're used in perfumes. Now, to prepare them, you would have seen this already in the alcohol section. You know that a primary alcohol, when it oxidizes, goes to an aldehyde and then to a carboxylic acid. So if we use acidified dichromate solution, we get our orange to green color change. Now, aldehydes, some uses of them, they're formed in whiskey barrels, okay, when oxygen slowly diffuses into the barrel. So what you've got is a very slow oxidation process. So when you do the oxidation with acidified dichromate and you heat it, it's quite quick, so your alcohol goes to your carboxylic acid. In a whiskey barrel, or in whiskey just in general, what they do is a very slow amount of oxygen getting in. So what happens is that very slowly it converts to the aldehyde first thing. That's the key part of the whiskey flavour. Also in our body, when we consume lots of alcohol, so the ethanol is converted into ethanal, and ethanal in you is what can cause severe headaches and nausea. So when you throw up from lots of excess drinking, that's due to aldehydes in your body, and when you get the headache from a hangover, that's also due to the aldehydes in your body. So this is a condensed equation over here, or an annotated equation, and you can see we're just going to get alcohol, primary alcohol going to the aldehyde with 2H plus 2 electrons. Obviously the other part of the half equation is from the dichromate, which I did in the previous video. Now to get the aldehyde, remember if you use oxidation of the primary alcohol with acidified dichromate, remember we said it'll go to the acid pretty quickly. So what we do is we rely upon the fact that the aldehyde has a lower boiling point than the alcohol. So what we do is we have a controlled reaction. Sometimes what you might actually see is they might actually drop the acidified dichromate in slowly to the alcohol, so it's a very controlled reaction. What we're trying to do is heat it up so we get just below the boiling point of the alcohol. So if we were using an alcohol with a boiling point of say 70 degrees Celsius, okay, we would heat it here up to maybe about 60 degrees or something like that. Okay, so we're trying to get the oxidation of the alcohol to occur. What's going to happen is that as the aldehyde is formed within here, alright, so if we've got the aldehyde here, because the aldehyde boiling point is lower, what's going to happen is that aldehyde is going to boil straight away. The aldehyde vapors are going to travel their way up here, okay, and they're going to enter into the condenser, where here in the condenser, where they come into contact with the cooler water, they're going to condense back into a liquid, and it's going to drip out here into our collection vessel. Now, because the alcohol has a higher boiling point, it's not going to boil over with it. So we just, as soon as the aldehyde is formed, it's going to boil. It's going to leave the flask. That's going to stop it from reacting with the dichromate, and it's going to allow us to collect it over on the side. Okay, so it's quite a good way of collecting it. Aldehydes can be oxidized either under acidic conditions or alkaline conditions. So when you oxidize them, it's just that second step in the oxidation of the primary alcohol. So we're going to our carboxylic acid. So if you do it under acidic conditions, you just end up with the acid. However, if you oxidize it under alkaline conditions, you deprotonate the carboxylic acid group. Alright, so you end up with the carboxylate salt here. Alright, and that's quite useful because in organic chemistry, when we have a carboxylate salt, we can add in, if we make it a sodium or a potassium salt, that makes it water soluble, so that's quite useful. Alright, so what they might ask you to do is draw the product of oxidation under alkaline conditions, so make sure you deprotonate the carboxylic acid here. There's a very good test for aldehydes, and we did talk about this just at the end of the alcohol section, and that's the Tollen's test. So the reagent that we use is something called ammoniacal silver nitrate, so it's a mixture of a number of different chemicals in together. It's a basic solution though, so you can see here that it contains hydroxide ions. Okay, so what's going to happen is this is just an oxidation again, so we're converting our aldehyde, okay, into a carboxylic acid, but because it's under basic conditions, we deprotonate the acid, so we get the carboxylate ion. Now what they like to do sometimes in the exam is ask you to draw the structure of the product of the reaction with Tollen's reagent, and so you need to draw the deprotonated carboxylate ion. The ammonium silver solution over here, ammoniacal silver solution, is what gives us our solid silver precipitate, and you can see this is a conical flask that I did a couple of years ago. You can see the quite strong silver mirror that's actually formed on the inside, so it's a silver precipitate which has coated the inside of the conical flask. Aldehydes are the only functional group that undergoes this reaction, so it's a really good test. Okay. Ketones, however, are formed from the oxidation of secondary alcohols, and they have the carbonyl group. So again, here's the carbonyl group. Propanone is the first one. They are not at the end of the chain, they're in the middle of the chain. Okay, so what you need to do is basically name where the carbonyl group is. Alright, so in propanone, there's only one place it can be, which is in the middle. Alright, butanone, whether it's on this carbon or this carbon, it doesn't matter, it's going to be the second carbon either way you look at the chain. This name here is probably actually missing something, so on the third carbon you do have this methyl group here, but the carbonyl group, well, in this case it's not missing anything in the name, because whether it's on this one or this one, it's going to be on the second carbon. But if there was another carbon group over here, if this was H like this, okay, you would then want to make sure that you put the number in on which carbon atom it's actually on. Alright, maybe have a look at the video just on naming aldehydes and ketones that I've got up on the website as well. Alright, so oxidation of your secondary alcohol under acidified dichromate, orange to green colour change, it forms a ketone. Okay, they're most commonly used as solvents. They're really good. So propanone here is also known as acetone. You'll find that in nail polish remover. Alright, really good because you've got these methyl groups on the end which allow it to bond to organic molecules. Alright, this carbonyl group gives a little bit of polarity, so it can also be a little bit soluble. So it's a good, really good solvent. Medicine, acne cream also contains some ketones as well. When your body breaks down fat for energy, so when your carbohydrate intake is low and your body needs to burn fat, it forms ketones as well. So that's basically aldehydes and ketones. Like I said, a lot of it is just some rehash of the alcohol oxidations. suggest you have look back at the Tollen's reagent test. Make sure you can know how to draw the structures of aldehydes and ketones. And as always, if you've got any questions, thanks guys. As in, if you've got any questions, just ask. I forgot to add that in.